Hey guys, how are you? It has been a long time. I have actually posted a video on the Coding Box YouTube channel, and that's also been because I have recently joined Zomato as the mobile platform team lead, and been working on the Zomato Android app, and we have released a new version. Maybe if you've got an update, you will see the new Zomato app, which has a completely new UI, completely new screens, all of that stuff. But yeah, finally got some time to make a video, and I want to talk about something. I usually talk about Android and web development, Vue.js, and all of that stuff. But I want to talk about something more basic, more fundamental today. That is what happens when you compile a simple C++ or a C file with GCC or G++. When you compile, what happens? Very interesting topic because I mean, sometimes I've seen interviewers ask things like this, and it's very good to know what really is happening. And usually in some of the interview preparation lectures that I've taken, I usually discuss this a lot. It's a very interesting topic, and I think a lot of you guys have been doing, data success algorithms, competitive programming, like you have been using C++ for 3 or 4 years. You're doing a lot of C++ programming, and yet a lot of you guys have not focused on understanding what's really happening underneath. So let's take a look at this. A lot of you guys might actually be knowing these things already, so that's fine. But it might come as quite a bit of a new learning experience for a lot of people. So let's take a look at this program, and it's a very simple program. It's a very basic program. It's probably the simplest program that you can build using C, which is an int main function which returns 0. So any program that runs successfully should return 0, and any program which does not run successfully should return a non-zero return code. And we can just click on run on VS Code like this, which basically does is basically do GCC source dot and source dot c and a hyphen o save program, and then it runs the program file, and it does nothing. It's just a return 0. I have not even done a C out hello world or something like that. Okay. um, so interesting stuff is what happens when we do this GCC source.co prog. What are the steps that are involved in this? This is not a single step operation. Okay, so let me tell you something. The first step that happens is GCC creates a proper source code file or an extended source code file out of this, which you can do yourself using the hyphen capital E flag on source.c, and you will get an output which looks like this. Now this output, as you see, contains a lot of lines, which is the name of the file, and which contains some flags like built-in and command line kind of flags like this. Well, these are some special compiler flags that the compiler inserts into your file. Also, an interesting thing is if you did have a library included into your project, like if you had include string.h, yeah. So in that case, the output of gcc-e source.c would look quite different. It would contain not just your source code and all of those extra lines earlier. It also contains the entire contents of string.h as it is copy pasted right here. So if I just take this and output and save it somewhere like source.e.c, and you can open source.e.c and look at all this source code out there. If I go to the source code of string.h, you will see that the source code of string.h contains all this stuff, which exactly has been copied down here, with the only exception that the comments from string.h are not copied. So there's this copyright from Apple, and there's these copyrights for string.h and ifs. These comments, as you can see, have not been copied. So it's only the runnable part of the code from string.h, like the meaningful part of the code, not the comments. Those have been copied, and there are these line markers that have been inserted here, which contains the names of the files that strings include itself. So strings includes common.h, and strings includes underscore strings.h. So all of these files that string.h has pulled along with itself into it have all been marked, and that's what you have got, this source.e.c file. The next step that GCC does is convert this into assembly language instructions. So you can do that yourself as well. You can write GCC, and in fact I will just remove this file for the moment, and I will remove the include line because I don't really need that. and I can write GCC hyphen capital S and write source.c. It gives me a source.s file. Now, although like you can see, this is not C++ code, but it still makes a little bit of sense because this is assembly language code, and assembly language code contains instructions like move left, move right, pop, push, and all of these instructions. So as you can see, this is the beginning of the function main. This is how you write commands in your assembly language code, and this is your main function. It pushes certain things, pops certain things. Okay, as such, if it does not make sense to you, that's fine. I mean, we are not here to learn assembly right now, but I'm just giving an peek into what really happens when you're compiling the file. An interesting thing is if I include the line that was there earlier in my file, and I just create a source2.s file. Source2.s has been created with the string.h file included, and source.s has been created without the string.h file included. And as you can see here, there's no difference between the two files, which means that if there are a lot of functions that are defined in string.h, if there are a lot of structs that are defined in string.h, but they are not used in your code anywhere, then the step of turning your code to assembly language code will remove all of those things. So the C++ compiler is smart enough, it can check whether a variable is used or not, whether a function is used or not, and it will not copy that into your assembly language unless they are really used. Okay, so yeah, I guess that's it in the assembler stage. Then what happens is GCC does the step where you get -c, and I can write source.s, I think, and that gives me the object code. So this .o file is a binary file. It cannot be displayed in the text editor because it's binary, but we can see the hex dump of this file, and it's a hexadecimal file, and it contains stuff like run the main function kind of instruction out here, all of that stuff, and it contains some basic elf code that usually goes inside every object code file. But this file cannot be executed right now as such. If I try to execute source.o, I'll find that, oh wait, permission denied. I can fix. I can set the permission 777 to source.o. Now, if I still try to execute source.o, we have exec format error. So this is not an executable format right now yet. So we can get to the executable format to .prog file, and if I take a look at the .prog file, that is also a binary file, and the source.o file is also a binary file, and there might be certain similarities as well. So you will find there's this unwind info stuff out here, and you would have an exact same thing with an unwind info in this file as well, and you would have this some this UHAG, this text written here. You would have similar things in your source.o hex dump as well. So there are certain things which are similar to the source hex dump, but the hex dump contains a lot of other things. It contains instructions with which it tells the operating system which libraries to link and which libraries to load and stuff like that. So that's what your hexadecimal code for the binary files look like. Now let's take a look at some very interesting stuff here. We're gonna go a little bit deeper and take a look at an interesting step here. Like if I write char h equal to, and so character array h equal to, okay. So what happens is if I write GCC and I write capital O0, which means don't make any optimizations, O0, and I write source.c and I output it to program. Okay, so I'll get to know that the size of my program is 8.3 KB in size, and my source code file is 57 bytes, and this prog file, if I see the hex dump, I'll see somewhere in this file there's gonna be this this character array which we have created and we have not used here. Now if I'll show you what the difference is. Like if I run GCC with O of 3, which is 3 optimizations, 3 level of optimization. So there are O1, O2, O3, 3 levels of optimizations that exist in GCC. There are a lot of different optimizations like removing unused variables, removing unused functions, short circuiting constants and stuff like that. So if I compile it with O3 and I save it to a prog2 file and try to see the data size, you will see prog2 is only 4.1 KB in size instead of 8.3. So in fact, if I look at the hex dump of this file and if I look at the hex dump of this file, this is the prog hex dump and this is the prog2 hex dump. As you can see, they start with similar things, but somewhere down the line the prog hex dump has more optimizations, as a result of which the file is smaller in size, while the prog2 hex dump does not have all those optimizations. It has the libsystem loader is written inside it, although the prog hex dump does not have them because it does not need to load the libsystem. And similarly, there's going to be some stuff during my execution code which is not needed, but prog2 has like removed those, but prog does not have them removed. So all that stuff is going to be happening. Now if I take a step back and see what's happening at the assembly level stuff, we can see exactly the differences. Say I write GCC -S and I write source.c and I output it to source.s with the optimization flag of O0, and I do it with source2.s and I do it with O3, sorry, with O3 let's do, which is the maximum level of optimization possible. And let's take a look at the source code file for these two things. As you see, the source code for source2.s looks like the assembly instruction does not contain the code for hello world at all, but the source.s file contains all of the codes for moving the character array and pushing all of these characters hello world into it, and there is an ASCII constant for hello world defined inside that. So as you can see, we can actually, like, if you pass the O flag during the compilation step, even during the assembly language creation stage, the assembly language file that has been created can be created in a more efficient way by GCC if it is running those optimizations on your code. Let's go and take a look at some more things. What happens when you create header files? So let's say I have a header file, lib.h, and what I do is I have a function called int sum, which takes int n and int m, and it returns m comma n. It returns my bad, it returns m plus n, right? And we have or rather I should say that I should just create this function declaration here. I should have a lib.c file where I should actually define this function. I should write return m plus n part here. That's my library source code. That's my library header file, and in my library source code I'm supposed to include my library header, and I should include my library header inside my source code file as well. And let's say I return the sum of 4,5. Okay. What happens when we compile it, of course, is we do GCC and we do source.c, and we will find that linker command failed because it could not find a file to link itself to. But if I write GCC source.c and lib.c, then it's able to compile them, and it's able to create an a.out file, which if I run a.out, it returns 9, which is of course the exit code for 4 plus 5, right? What happens when we write something like this? Let's see, I do GCC -e source.c, and let's output it to source.e.c. The source.e.c contains the source code, plus it contains the contents of lib.h, which is this line. Okay, similarly I can do GCC -e lib.c, and I can paste it to lib.e.c, and as you can see, lib.e.c will contain something similar. It contains the source code of int sum, and it contains the function of that, right? We can convert these to assembly language programs as well. I can do GCC -s capital S source.c. If I do that, the source.c assembly language thing, it would be containing some assembly language instructions. And the interesting thing is, if I just assemble the lib.c file, and so this lib.c file in the source code has the sum function, which is global function sum, and it contains the definition of the sum function, as you can see here. Now the assembly language version of source file, you can see there's a call queue to sum, as you can note here, but sum is not defined anywhere. This is the only instance where sum is defined. So call queue to sum can only run if the global sum has been done. Okay, so these two assembly language programs, they have been compiled, they have been converted to assembly language, but they can't actually run because there is something defined here which is getting called here, and they are not in the same place. We can in fact get to the object code part as well. We can write GCC -c, and we can write source.s, and we can get the object code for source, and we can write GCC -c and lib.s, and we can get the object code for the lib, which is this is the object code for lib.o, which contains the sum function, and this is the object code for source. This contains the main function inside it. As you can see, it has a call to the main finally, and the lib.s, the lib.o. Yeah, so this is the lib object hex dump, which contains the sum function definition out here. Again, up till the object code, again, these two are not executable right now, but I can do GCC lib.c and source.c, and then we get finally an object code file where it contains the the entire code base. This contains the output of lib.o as well as the output of source.o, and both of them together put into a.out. Now if you look at the just take a look at the data size that we have gotten. So the size of a.out, which is my final output, is 4.2 KB in size. The size for my outputs, lib.o is 624 bytes only, and my source.o is 668 bytes right now. Okay, and one interesting thing is, if I in my source.s file, source.c file, if I do not return sum45 and I simply return 0 here, although I have included lib.h. Okay, so I've included lib.h, and if I want to, I can call sum, but I'm not calling sum. And in this case, if I do GCC and I run source.c and I output it to just do source.c, you can see it gets compiled. So if I include a certain library, but I'm not calling any function from that library, I've not called the sum function. At that stage, I can actually compile my source file directly to a executable, which as you can see actually does run, because there are no calls to any lines actually. But if I have, say, int x equal to sum of 1 comma 2, something like this, and as soon as we run that, so symbols not found for architecture, we have problems like this. So underscore sum is not found because I've not provided both the C files to it for it to compile. If I pass optimization 3 to it, I'll still have that problem that the sum thing has been passed to it. Okay, if I do GCC -s and I do optimization of 3 of source.c and look at source.s file. Now here's an interesting thing here. If I had written int x equal to 10 here, or int x equal to 3 instead of sum 2, and I do this gcc -s o3 source.c, this variable x that has been created here, there is going to be no proof of that inside my assembly language code at all. So you look at the assembly language code for this, and if I remove this line, right, and I turn it into assembly language once again, you will see the assembly language code remains exactly the same. Because the compiler knows that this line has no purpose here, because we are not using the value of x anywhere anymore. But if instead of hard coding the value of 3, we write sum of 1 comma 2, right, so in that case, if I do gcc so3 source.c, in that case you will see that the created assembly language code contains a call to sum. Now this is interesting because the compiler, when it's running this line, knows that x is not used anymore, but it does not know what the function sum does. Okay, so maybe the function sum internally has some printf lines, or it's treating these variables by instead of by value, they are treating them by address. And if they're doing such a thing, in that case, omitting this line during optimization is not a valid solution. Okay, so what would happen is that the final code for assembly language would contain the call to sum still there. Okay, let me just say, if I return x here and I compile source.c and lib.c with optimization flag 3 on, then the size of the a.out file that I get is 4.2 KB in size. And instead of that, if I return 3 here and not actually use the value that's written here at all, and I still did the same thing, gcc03 source.c and lib.c, and if I try to find the data size here, you'll see again the similar thing happens. Even if the compiler has visibility of both the lib file and the source file, function calls will not get dropped automatically, because there is no guarantee that what happens inside the function call. But if it were simply a constant and this constant was never used again, so those things get dropped during these kind of optimization. So I think this gives you a fair bit of idea what happens during the compilation stage. So there is the stage where your source code file gets converted into an extended or proper source code file, which includes all the headers. Then it gets converted into some assembly language and this assembly language is going to be platform specific in nature. So if I did the gcc -s step on a Windows machine, or on say a 32-bit machine versus a 64-bit machine, so this thing that has been generated would be different for different machines. So at this level, the code already is platform specific in nature. The build version would not be macOS if I was using a different version of GCC. Okay, and then this assembly language thing is converted into object code. Object code is already machine readable code, but the file is not executable yet. The operating system would not know how to link or load libraries and how to execute any line inside that. And then finally GCC turns it into an executable code, which is usually called a binary ELF format in Linux and Unix based systems like Mac, which I'm using. It turns into ELF format, which is the a.out file here, which basically you can actually execute using running /a.out. That's all the steps that are happening. It's good to have a basic overview of that. This is a short video. I didn't have the time to really go into that in any further depth, but if you're really interested, you can study more about compilers, how GCC works, what are these steps happening, what is compile proper stage, what is the assemble stage, what is the linking stage, what's the loading stage, and all that stuff. Okay, hope this has aroused in your curiosity a bit. You can look up these things maybe on your own. If you have any doubts, any issues, any questions, please feel free to write them in the comments. Thank you so much for watching the video.